Good afternoon, everybody, and thank you for being here. Well, as it has been said, I'm going to talk a little bit about Titan's experiments that we have developed in a collaborative program under the University in Mexico and LISA in France. So Titan, as most of you well know, is the biggest satellite of Saturn. It is known since 1655, and it is the main feature that calls attention is the existence of an atmosphere around it, discovered by Comas-Solá since 1907. In the area of the Voyager studies, we know that Titan holds a dense atmosphere mainly formed by nitrogen and methane, and that it was converted to hydrocarbons and nitriles. And due to the information that was coming up since the 2004 by Cassini-Huygens mission, we now know that Titan also holds liquid reservoirs on its surface. And there is a lot of information coming up from this mission about Titan. So we like to know, or we like to see Titan as a planetary refractory of organics, and everything started in the very up layers of the atmosphere, where the main constituents are transformed continuously by solar UV or solar photons, and also energetic particles coming from Saturn magnetosphere, for example. And these methane and nitrogen are converted, as shown before, in mainly hydrocarbons and nitriles that continually evolve chemically and are transformed into heavier compounds, aerosol or compounds like this, that can precipitate down to the surface and can be deposited. Of course, there are other features or cycles here on Titan also occurring, like, for example, the methane cycle that is close to or is similar to the water cycle here on Earth. So, another important feature here in this satellite is the possible existence of an internal ocean. In one of the previous talks, something was mentioned about this. It is proposed that this ocean could be below 400 kilometers or 40 or 100 kilometers down in the surface. It depends on the model that you use to justify this dip. And there are a couple of important information that can use to justify the existence of this satellite. One of these is the latest observations of Cassini around features that move quite quickly, or more quickly than expected, on the images that were observed, that cannot be explained only due to movements of the atmosphere, and that means that the surface must be decoupled to the interior of the satellite. The other evidence is the existence of certain extremely low frequencies that cannot be observed without the reflecting surface or something that is reflecting on the surface of Titan. Of course, the surface, as we know, mainly covered on organic materials, cannot be a good reflector for these observations. So it is proposed also that this water ammonia ocean could be the source of these observed reflections. So if this internal water ammonia ocean exists on Titan, can it also exist phenomena like cryovolcanism or things like this that put this out of the surface? And this is thought mainly, or the initial thoughts mainly were related with the changes in opacities, bright and dark areas observed on Titan. So here it's only a sample of all these geological features that now are known that exist on Titan. So we have information about the presence of lakes, mainly hydrocarbon lakes, enriched probably with some nitrogenated compounds. Dunes that are, there is an equatorial belt of dunes existing around Titan, the existence of hazes, of course, in the atmosphere, dunes, canyons, and volcanoes, and all of this information come from the instruments in this Cassini-Huygens mission. So, oops, something happened here. Okay, it was supposed to appear later, but the idea here is that we focus on these kind of features, the existence of cryovolcanism, as I mentioned before, and the sporadic existence of impact craters created on the surface of Titan. So when the aerosols, atmospheric aerosols, deposit and arrive to these places, they can meet or they can get in contact with this interior water ammonia mixture. So the main question of our work is that if these Titan's aerosols can interact in this kind of surface deposit and form or produce astrobiological interesting molecules. So for this, we have this experimental setup. So we use a setup at LISA and Curtail 12 University, and it is a setup that is basically a continuous flow moving system that has a mixture of nitrogen and methane irradiated with cold plasma discharge or electric cold plasma discharge. We have performed experiments at a low temperature and also low pressure. We have here more details about experimental details like the power deposited and the time of the irradiation. From previous reports, we know that these cold plasma aerosol analogs are or contain a higher nitrogen accumulation of in the material form. They are complex it's a complex mixture of organic compounds. There are still discussions about if this is a heteropolymer or a polymer or an amorphous mixture of organic compounds, but something that is clear is that they are of refractory nature. It means they are very stable in higher temperatures. When they are pyrolyzed at 600 degrees, they mainly produce HCN and NH3. And it happens to be that these characteristics are very similar to the characteristics of the aerosols in Titan, according to the information provided by the Huygens probe. So after we produce our aerosol analogs, we recover them and we place them in conditions for suffering alkaline hydrolysis. So we, as the quantity or the concentration of ammonia is not known on Titan, it doesn't matter what is the origin. We propose a different set of concentrations of ammonia from 25 to 3%, and we subject this mixture of hydrolysis ammonia and well, it's ammonia solution, so there is water there, to different temperatures, cold temperatures. And we put all this mixture in closed vials, as you can see here, during 10 weeks. As I mentioned, the exact nature of the Titan aerosol analogs is not known, but several pieces of information coming from spectroscopic studies show that they can contain aliphatic or aromatic hydrocarbons inserted, nitrile or imine, amine, carbodiimine, and cyanamide signatures. And these chemical groups are very reactive towards conditions like the one that we place here, alkaline conditions. So the kind of compounds that we form are derivatives of this style, and they are formed with the interaction of our hydrolysis products with these substances. It's also a very long name, so I also use this group of letters to show it. And the idea is to modify the refractory nature of the derivatives that the compounds that we have from the hydrolysis. So the derivatives that we form are better to place until the chromatographic conditions. That is the technique that we use to identify this compound. So I am showing here a chromatogram. This chromatogram is coming from the experiments at the lowest temperature that we used. So you can see that there are very tiny peaks representing here the different compounds. We identify by this technique 7 amino acid derivatives, and also perform, as it was a coupled technique with the mass spectrometry, we also perform a quantitative study. So we have here all the 7 compounds that we form, the 7 amino acid derivatives, and also we have urea. And you can see from here That the main compounds, the ones with the highest yields, are precisely urea and glycine and alanine. Something that I can also mention here is that as low as you have the temperature in the experiments, the yields, generally speaking, are also lower, no matter how much ammonia you use. But nevertheless, we have an important formation for these compounds. Also, we have interesting chemical characteristics in the amino acids that we form. We have methyl ramifications, we have an heterocycle amino acid, and also an amino acid with a hydroxyl group. The details about the mechanism of formation for this are not really very clear yet, but this can mean that this chemistry that can be developed here is very interesting and deserves a little more detail, detail in study. Here it's also a complementary study performed in the group where we analyze the reactivity of the toluenes, mixing them with water at room temperature, well, not room temperature, sorry, but a temperature higher than the temperatures that I just mentioned before. And the results are important because exactly they show how reactive can these products, these toluenes, these aerosol analogs can be. So moving this to the Titans scenario, we can see that there are two places right now in Titan where there are more probabilities to find this cryovolcanism phenomenon. And we know also from previous study that more or less we can have a max flux deposit of aerosols on Titan on this range. So if in a period of time not long enough for the solar system life and so on, we can accumulate a considerable quantity of aerosols. If this, we can have quantities that can be detectable with the current technology, so it could be interesting for future missions or for understanding better the results of the Cassini-Huygens instruments. And well, I stop here, and as a conclusion, I can say that we have demonstrated that they can, that the analog aerosols of Titan can form astrobiological interesting compounds when placed in water ammonia solutions. Also, we have found that this hydrolysis is faster when exactly we use the combination of water and ammonia and not with water alone. And the chemical transformation is done even if the temperatures are low, as close to temperature, to the temperature on Titan. And of course that we think about that we cannot be the very end of this set of reactions occurring in the satellite, and that probably some other mechanism as the presence of energetic cosmic rays can still provoke some other transformations of Titan's material. Thank you very much, and thanks for your attention and the organizers for the opportunity to be here today.